We are live. Okay, let me just put my microphone inside my mask so those of us who are listening at home can hear me. Okay. All right. Okay. Yeah. So this is, like I said, this is like the tentative course outline. It's extremely long, much longer than I would ever make a syllabus if there wasn't the requirement to have all of these little things included in it. And I'm not going to read it like word for word. You guys are perfectly capable of reading, after all. But I will post it on Classroom once it's officially approved. I kind of want to give you a brief overview. Like I said before, there's a few things in particular that I think you should know. So yeah, like you may already know, there's the AB and the BC different portions of the calculus course. We're teaching them simultaneously. Some schools, if there's like a whole bunch of AP students, they might split them up into AB and BC. But we're just doing it all together in one class. So that means for you, you can sort of decide if you want to do AB or BC throughout the year. I'm hoping that sometime, maybe by February, you've determined what you like to do, and I'll kind of explain the differences in those two courses in this document as well. So AB is basically like a first semester calculus course, and BC is like a first and second semester course. So I've got a whole bunch of stuff about expectations and all of that, but you don't need to know about that. One slight difference is, I think in the past I've recommended that you have a calculator. It turns out that that is actually a requirement. So so you are required to have a TI 83, 84, the pluses versions of those, or an Nspire calculator. If you are unable to get one, I have some extras. You can borrow them for the remainder of the year. But yeah, it is a requirement. So we'll talk a little bit as well about what's allowed to be used on a calculator. So we will be writing some programs for our calculator that will help us sort of visualize some of the concepts in calculus. But on a test, there's the 4 functionalities. This is kind of like an AP College Board sort of phrase. So these are the 4 things you're allowed to do on a test. So you're allowed to plot the graph of a function within an arbitrary viewing window. Basically means you can graph functions. You're allowed to find the zeros of functions. So essentially solving an equation. So you can get your calculator to solve an equation for you. You can numerically calculate the derivative of a function. You probably don't know what that means yet, but we can take derivatives on our calculator, and we can take a definite integral. Don't know what that means yet either, but you will before long. And this is kind of just more stuff for you to read on your own time. This is the primary textbook is Calculus Concepts and Calculators. That's the one that you have a hard copy of. I believe everyone has a hard copy of it, right? Yeah, I think we're good on that front. And then we are also going to have a secondary book to supplement, which is just called Calculus, and that is that one. And I will be, I mean, that's kind of the work stuff that we've been working on so far has been from this book. Okay, so this is we just have digitally. And then, yeah, as for additional resources, I think I've mentioned a few times that you can always get help from me in period 5. So if you would like to use Discord, that tends to work best for me. But if there's another platform that you prefer to use, I can work around that. The College Board also offers videos on AP Classroom. So I think almost all of us are signed in to AP Classroom. I think there's 15 of us, but in total we have more than 15 students. I believe we have 19 students. So 4 of us still need to get on. I haven't figured out who you are, but if you haven't signed up for AP Classroom, please do so as soon as possible. We will be using that very shortly. I guess I should have talked a little bit about AP Classroom in here. But AP Classroom is basically, it's a proprietary sort of classroom website, but it's made by the College Board. And I will be posting what's called a personal progress check at the end of, well, about halfway through a unit, and then at the end of a unit. So about halfway through the unit, you'll be able to sort of see how we're doing so far. Yeah, and feel free to take pictures of this if you like. And then at the end of the unit, just to sort of wrap things up. Okay, so the course outline and pacing. So this is the stuff that I'd really like to sort of make sure that we're aware of. I also want you to understand that this is very much subject to change. Yes. Yep. Yes. Yeah. Yeah. So the part of your grade will be determined from the progress checks. Yeah. I don't know. Pardon me. Uh, So I mean, ideally, it would be each unit would have a unit test. So in the past, we would just do 10 tests, and that's where the majority of your mark would come from. Another part of your mark would come from um, the progress checks. But typically, I would have, yeah, just a test. What I'm thinking of for tests is just to sort of treat it more like an assignment that you would have for about 24 hours. So I would give it to you on Google Classroom, and you'd have 24 hours. And I suppose that would sort of open up the possibility to collaborate. But I think that's just how we're going to have to work with it. So yeah, your grade will be determined from um, the tests and progress checks. Totally. Yeah. Yeah, that also doesn't make a lot of sense. Yeah, I think that just giving you 24 hours, or maybe even like giving it to you on a Friday, right after school, and then having it due on Monday. That way, everyone kind of has the same sort of time frame. Because even if you have 24 hours, it might be unfair to those who have to attend school, right? Because then they'd be busy, right? So there's it's definitely challenging, but yeah, that's what I'm thinking of in terms of the format would be a take home test. So all these would be take homes. Yes, yeah. So all the stuff that I've posted so far is just for your own practice. And so far, this it's still not quite like calculus. The beginning of like this is still algebra. This is like working with functions and stuff, rearranging functions. Calculus begins with a thing called a limit. So if you're not including anything with limits, it's not calculus. So pretty much all of this stuff from unit 1 through unit 10 involves a limit in some form or another. So that's really what calculus is. It's about limits. So since we haven't learned what a limit is, we haven't technically done calculus yet. So we're still kind of doing some reviewing and stuff like that. You may have noticed as well, I posted a chapter on trigonometry. So just from sort of conversations that I've had with the different clusters, really anecdotally, like I don't have hard evidence, but I get the impression that trigonometry is a challenge. I think that it may not have been covered very thoroughly last year just because of how crazy everything was. So I posted a chapter on trigonometry. If you're struggling with trigonometry, then I'll ask that maybe you start doing one section at a time. I really don't want to overwhelm you. I would imagine that you're very busy and that you're getting lots of homework. I know that I have assigned homework pretty much every day so far. So I don't want to pile on so much that you become like really stressed out and start hating math. But it is important that we work through that because trigonometry is a really important topic in calculus. So I'm hoping that we'll find some time before we actually start doing trigonometry in class, like throwing calculus at it. Because if you have any challenges with trigonometry before we start throwing calculus at it, then it's going to be really unfun. So yeah, we'll get to that momentarily. So yeah, like I was saying before, So these time frames are very approximate. It depends on a lot of things. There's a lot of variables in here. But that's kind of the general idea of how much time we'll be spending on these. So yeah, that's. I mean, I don't even know why I included it. But yeah, I mean, for instance, this is our biggest topic, integration. This is one that's going to take the most amount of time. So we'll ideally spend about 1 full month on integration. Um, yeah, so this is just kind of saying, it's important that you do your work. Progress checks will be provided in class or as homework assignments. We might be doing some things in class for the progress checks. I might just leave it at home, especially since there's only going to be 1/3 of us in here at a time. So if I do it in class, then the other 2/3 of you will be doing it at home. Um, this is kind of more like an AP College Board thing, the mathematical processes. I like it. I think it's cool, but I don't think you guys really need to know too much about it. This is more the College Board making sure that I'm teaching in different ways. So there's different practices. One of them is implementing mathematical processes. So that's like doing like an algorithm, like long division or something. Obviously, we wouldn't be doing long division, but well, we might, but just a process. Can you complete a process? And then these are some sample activities. This is why this thing took so long, is because there's these sample activities. So those are some examples of where you might be asked to do a process. Connecting representations, so like representing a number in several ways. And again, these are more activities. Like this is the sort of thing that if it was up to me, I totally would not include this in a syllabus because it's not really stuff that I think you need to know. We're gonna do it, so you don't need to know all this stuff, but it's all here. Justification, so doing some reasoning, like explaining yourself, communicating with others, that sort of thing. And then communication and notation, so being able to like read and write mathematically and communicate with your peers. Um, and then this part right here, I think, is actually really important. This is actually kind of a little bit hard to find. I mean, well, it's not that hard to find if you know where to look, but I'm happy to just be able to give this to you, the unit index. So this is just all of the different topics that we'll be covering this year. So like I said, you will be getting a copy of this. I will post this on Classroom shortly, but I do want it to be approved first. So the first unit is limits and continuity. Then we have differentiation, and there's a whole bunch of sort of subunits. Differentiation, some more differentiation, lots of different types of differentiation. What did I copy? Oh yeah, this is not right. Oops. So maybe I should quickly change that. So that should actually be. I think this is. Shoot, I don't remember what this one is actually supposed to be. So yeah, I will fix that before I post it on Classroom. Then integration. This is our big unit, the one that's probably going to take the most amount of time. Um, Differential equations is a good one as well. I really enjoy that topic. More integration. So you can see integration is huge. Some of these things, like we might kind of cover several topics in one day, like volumes. There's a whole bunch of different volume types of questions. So we might just that might be like one class kind of thing. And then Unit 9 and Unit 10, these two units are omitted if you do AB calculus. So if you're not doing BC and you decide to do AB, then you omit the final two chapters. And that's the only difference between AB and BC, is these last two chapters. So another thing that I threw in here as well is the exam weight. So this is sort of approximate numbers, but this is from the College Board. So it kind of gives you an idea of how much emphasis there is on each of these topics. So this is the AB exam, this is the BC exam, and this is each one of the units on the rows. So the last two, since they are not on the AB exam, then there is 0% weight. But This is just approximate numbers of what you can expect. So again, integration and accumulation of change, it's about 1/5 of the exam for both of them. So really, really big topic. So yeah, so that's the syllabus. That's all there is to it. It's 8 pages. Definitely the longest syllabus that I've ever given to my students. Like I said, I usually try to do it within 1 page. Of course, like this, honestly, I would probably do 2 pages because there's a lot of information. But still, 8 pages I think is too much. But yeah, and I already found a typo, right? I gave myself the wrong title. Let's see if I can find out what it is. Unit 5. Analytical applications of differentiation. So that's what it should have been. Analytical. Where I did contextual. Anyways, so I will post that on Classroom once it's approved by the College Board, and we'll take it from there. So let's do some mathematics now. So I've been posting some videos every day and posting a little bit of homework. I'm hoping that you're able to sort of keep up with that. If you're finding that the videos are too long, or maybe there's too many of them, like if every day is just too much and you're finding yourself to be a little overwhelmed, don't hesitate to tell me. Like I'm not going to be angry or unimpressed with you or something like that. The purpose of me making these videos is for it to work with you, right? So if it's not working, let me know, and I can try to make different arrangements. But so far, this is kind of what makes the most sense to me. These AP classes, there's really no changing the content, right? So we can't just sort of ignore a few of the chapters just for the sake of time. We do need to get through all of this material. So time is kind of against us. I only get to see you 1/3 of the time, but we still have the same amount of material to cover. So we are going to have to move rather quickly. So I think this is probably the best way to do it. But if you're finding that it's too much, let me know and we'll see what we can do. Okay. Okay, so I've got 2 functions here. One is sine of x, and one is cosine of x. Okay. So, oh, by the way, you might notice, and if you're watching the video, you can't see this, but um, I have 2 little cork little bulletin boards there that have just a little bit of information on trigonometry. So you may find those useful if you're a little rusty with trigonometry. So there's some formulas, there's a few important graphs, and the likes. So if you would like me to print those bigger, I can. I just printed those from our printer in the office, so they're not very big. So if you'd like me to print those bigger, I can make some big ones so you can see it from everywhere. It might be a good idea to memorize some of those things, and then you don't always just want to memorize something. You really want to be able to understand it. But for the time being, a quick memorization might not be the worst thing in the world. Um, Okay, so I've got 2 graphs here. One is sine of x, the other is cosine of x. And I want to think about the different symmetries of these 2 functions. So how are these 2 functions symmetric? Okay, so I want you to think about that for a second. And then we'll just have a little discussion about the symmetries of these 2 trigonometric functions. Does anyone see any symmetries? Yeah, they're the same, except one is shifted. Yeah, it is actually true. Yeah, that's a good point. That sine of x is equal to cosine of x plus pi over 2. Or I should say minus pi over 2. Okay? So that's absolutely true. They're related. Absolutely. Okay? What if we were to restrict just one of them? So instead of comparing them, what if we just thought of one function at a time? Like what are some of the symmetries that you might see in y equals sine of x? Like if we just focus our attention on this graph, what are some symmetries that you might be able to see? Yeah, they have the same range. So you mean like so the range on this side is like the same on this side? Is that kind of what you're saying? Yeah, exactly. So the amplitude on the right hand side is kind of like the opposite amplitude on this side, isn't it? Right. So if we were to sort of take a look at this value like right here, anyone know what this value is here? Like if we took a look at the peak of this wave, do you remember what value that would be? What about right here when it crosses the x-axis? Pardon me? Yeah. So the y value would be 0, but you know there's a what I mean here is like so this is the value 1, this is the value 2, this is the value 3. What at what value does it cross the x-axis? Like which value of x would that be? Say that one more time. Pi over 4. Okay, so so remember pi is approximately equal to 3.14. So pi over 4 would be a little bit less than 1, right? So that would be less than 1. So 1 is right over here. So it doesn't quite cross the axis anywhere in here, right? Well, yeah, let's because this is like the value 3. It's just a little bit more than 3. That's 3.14. So sine, I know that sine of pi is equal to 0. Okay, sine of pi is 0. So here's pi right there. Here is negative pi. Negative pi is over there. Okay. So what value would be right here? Yeah, it'd be pi over 2. Pi over 2. And then this over here would be which value would this be? Right at that peak? I shouldn't actually do it right on the line. It's a little bit to the left. Yeah, it'd be negative pi over 2. Okay. So let's think about the symmetries here. So if I go over pi over 2 to the right, then my y value, I guess you can't actually see any of these y values. Does anyone happen to remember what the range is for the sine function is? Yeah, it'd be 1 and negative 1. Yeah, so here would be the value 1. This would be the value negative 1. I'm going to make that a little bit further so it doesn't look like it's negative 1 there. So there we go. So yeah, we're going from negative 1 to positive 1. So if I go over to the right by pi over 2, then I end up going up 1, right? Now if on the other hand I go to the left pi over 2, I end up going down 1. Okay, I want us to just to think about that and think about how we could describe that symmetry, right? Because there's some symmetry in there, right? So symmetry kind of refers to like things doing the same thing in opposite directions, right? So let's think about the symmetry of this graph now. So this is the graph of cosine of x. So this is y equals cosine of x. Let's think a little bit about what this graph has in terms of its symmetry. So I can see something pretty symmetrical right around here. Does anyone else see that? Yeah, right. It's there's some direct symmetry. It's like there's a mirror right in the middle of the graph, right? So right at the line x equals 0, there is a line of symmetry. Okay, so that means like if I were to go over to the right, how far would this be? Where it crosses the x-axis for cosine of x? Yeah, it'd be pi over 2. So if I were to go over to pi over 2, I cross 0. And if I go over to the left pi over 2, I'm also going to cross the x-axis, right? So there's some symmetry there. This time it's exactly the same kind of symmetry, right? If I were to go over, does anyone remember how far this peak would be? 1 pi, right? Yeah, 1 pi. So full pi. And then the same thing over here on the left, we would have negative pi, right? So if I were to go over by pi to the right, I would achieve a value of -1. And if I went over to the left by pi, again, I would be at -1 again, right? So really similar types of symmetry, but fundamentally different, right? So we have a word for this. We have words for this. So we call the first type of symmetry, we call it an odd function. So the symmetry here, we describe that as an odd function. And an odd function says that if I take a function and I compare it with the negative of that same value, what ends up happening is that one of them will be negative. Okay, so that's the relationship here that we have with sine of x. Sine of x is an odd function because if I decide to go right by pi over 2, well, I know what I'll get. I'll get +1. But if I decide to go in the opposite direction, left, well, then what I end up getting is the negative version of what would happen if I had gone to the right by that much. So that's what we would call an odd function. And there are many, many odd functions. And these odd functions are really going to help sort of simplify some of our work when we start dealing with something called integrals. So if we can recognize odd functions, that will really simplify a lot of our work. So that's the symmetry of an odd function. An even function is the second type of symmetry. So this is an even function. And an even function says that if I take a function f of x and I compare it to the negative version, nothing changes. That f of x is the same as f of negative x. So if I decide to go in the opposite direction, it's just like if I went in the same direction as I started. So it doesn't matter if you're going to the right or to the left, the same thing happens. Okay, I want you to think about two functions. I want you to give me an example. Two functions. One of them, an odd function. Another one would be even. So think about where you might have seen an odd or an even function before. So I'll give you a minute to think about that one. And there's an infinite number of odd and even functions. There's no limit to them. I wonder if you could find one, though. Any thoughts? A parabola, yeah, yeah. So something like y equals x squared, right? And that makes sense, right? Because let's use the function notation. Let's call that f of x equals x squared. So let's see if it works with our requirement that for an even function, if I take the negative, I should get the same thing as if I had taken the positive, right? And I think that we probably would, right? So f of negative x would be, well, negative x squared, which is the same, that's the same thing as positive x squared, right? So that is an even function. What about an odd function? X cubed, let's see if x cubed would be. So let's try f of x to x cubed. Well, let's see what happens if I take f of negative x. Well, that's going to be negative x cubed. And, well, that's the same thing as negative 1 cubed times x cubed. And negative 1 cubed is negative 1. So, yeah, this is negative x cubed. So, yeah, that would be the requirement, right? Because this is the same thing as negative f of x, right? So f of negative x is negative f of x. So you can probably see why we call them odd and even functions. Is if we have a polynomial that is just a single term polynomial of an odd degree, so something like x to the 7, that's an odd function. And x to the 8, that would be an even function. Okay? There's many other types of odd and even functions as well. Like, for example, the trig functions that we looked at just a moment ago, those are odd and even functions too. There's many ways of making an odd or even function. A straight line like y equals x, even if it has a slope. Well, let's see. Let's try. So let's try. You have like a suggestion, or do you want me to make one up? Okay, let's try f of x is equal to 1/3 of x. Do we want it to cross at the x-axis, or sorry, at the origin, or do you want to have like a y-intercept somewhere else? Okay, let's see what happens if I have a y-intercept at 2. Okay, so let's see if this is even or odd or none. So what we would do is we would plug in negative x. This would be 1/3 of negative x plus 2. And this was then going to end up being, this is negative 1/3 of positive x plus 2. Is that related to f of x at all? Yeah, yeah. So the x is this is positive now. Let's head over to Desmos and take a quick gander at what this function looks like. Even though even though we already know more or less what it looks like, so let's try f of x equals, what did I say, 1/3 of x plus 2. Okay, and then I'm going to write f of negative x. Okay, so just looking at it visually, we can see that they have the same y-intercept, right? They cross the x-axis. No, not y-intercept. Yeah, yes, y-intercept. They cross the y-axis at 2, right? At the point 0, 2. But our symmetry, we want our symmetry to be focused at the origin. So we want our symmetry to be centered around 0, 0. So our symmetry isn't quite centered around there. So if our linear function has some symmetry, we want it to be at the origin. Does that make sense? Sort of? Yeah. So it's only going to be an odd function if the y-intercept is at 0. Okay? And you can I'm having a hard time here. So you can kind of see why, because if we want, so let's just say, for example, so let's try to find the y-intercept of an odd function. Okay? Let's see if we can find the y-intercept of an odd function. And this is any odd function at all. Okay? So the requirement of an odd function is that f of negative x is equal to negative f of x. Well, the y-intercept occurs when x is equal to 0, right? So let's see what happens when x is equal to 0. So we should have that f of negative 0 is equal to negative f of 0, right? So we want, oh, well, what's f of 0 then? Or sorry, what's negative 0? Well, that should be 0 itself. So we want f of 0 to be equal to negative f of 0. What number is the same no matter if it's positive or negative? 0. It's got to be 0. Yeah. So the only way that this equation is satisfied, right, is if these two are the same number, both positive and negative, and 0 is the only number that satisfies that. Another way of saying that is that you could say, okay, well, maybe I'll add f of 0 on both sides. So plus f of 0 on both sides. That means I would have now 2 times f of 0 is equal to 0. Well, then you could divide both sides by 2, and you'd have that f of 0 is equal to 0. So no matter if you're, it doesn't matter what your function is, if it is odd, it must cross the the y-axis at 0. Okay, and a really similar argument would exist for even functions as well. So even functions, or sorry, no, that's not true. That's not true. Never mind that. Even functions can cross the y-axis anywhere you want. Okay, so this is only a requirement for odd functions. I'm not quite sure if that answered your question, but maybe it was an interesting discussion. Okay. So we've got odd functions, even functions. There's one more thing I'd like to talk about. Okay. So I want us to observe this this graph here. Oops. There we go. So here's our nice little graph. This happens to be the graph y equals x cubed minus 3x. So here's our graph. So it's a cubic graph. This also has some symmetry. This happens to be an odd function, right? If I sort of like go down in this direction, it's the same thing as going up in the opposite direction. So this is an odd function. It happens to be odd. Okay. I want us to focus on 3 separate intervals though. Okay. So I've got 3 separate intervals that I want us to look at. This first one here is what happens from negative infinity up to negative 1. The next interval is from negative 1 to positive 1. Oops, that's not what I wanted to do. I've got negative 1 to positive 1 from here to here. And then finally, I've got positive 1 to infinity. Okay? So I want you to think about how could you describe those intervals? Like what's happening on those intervals? Yeah, I even color coded it. So any suggestions for the first one in this first red interval from negative infinity up to negative 1? Could we describe sort of what's happening generally with the graph? Okay, let's think about that. Let's think about that. So I want us just to consider that because that's a really good point. So we've got this arrow, right? And that's kind of what you're looking at is this arrow. And the arrow is it's kind of going in two directions, isn't it? Right? Like it's not going like directly down, it's not going directly left. It's kind of, even though it looks like it's mostly going down, it's still sort of going in a diagonal motion, right? So it's going a little bit left and a little bit to the right. Okay. So would you say that over here the function is increasing or decreasing? Decreasing. So we're thinking that this is decreasing. So let's think about this for a second. Okay, let's think about that. There's some deception going on here. There's some deception. The deception is that this arrow is pointing in that direction. In a graph, though, we always read a graph from left to right, just like we read words. So even though the arrow is saying, okay, well, the graph keeps on going, we're still going to read the graph from left to right. So if I had to think of like an initial point and an ending point, I would have to have the initial point to the left and the second point to the right. So when I go from left to right, am I increasing or am I decreasing? I'm increasing, yeah. So it's a resounding agreement that if we read it from left to right, it's increasing, okay? So in this first portion, the graph, in fact, is increasing. Increasing. What about the pink motion? Are we increasing or decreasing? Yeah, from here, because if we're reading it from left to right, we are decreasing. And from 1 to infinity, what's happening? Yeah, it's increasing again. Okay, great. Okay, so let's come up with a definition of increasing and decreasing on an interval. Okay, and this is a definition that we will refer to quite regularly. Okay, so a function is said, oh, excuse me, my phone is ringing, I'll just turn that off. A function is said to be increasing on an interval a comma b if for any x1 and x2 such that a is less than x1, which is less than x2, which is less than b. So basically what I'm doing is I'm finding I'll draw a little diagram just to sort of give you an idea. So here's my values of x. So here's my interval a to b, and I'm just finding two values of x between a and b, where x1 and x2 are such that x1 is less than x2. They're both values in the interval, and x1 is smaller than x2. Okay, so effectively what I'm doing, if we want to look at the graph, is saying, okay, here's my interval from -1 to +1. I'm going to find two values between 1 and -1. Okay, how about here and here? Okay. Okay, so if it's increasing, we must have that f of x1 is less than f of x2. Okay. We say that f is decreasing if f of x2, or sorry, x1 is greater than f of x2. So that's sort of the algebraic interpretation of increasing and decreasing. Okay? Okay, so that's really all I wanted to show you today. So I'm going to end the video there, but I'll still be talking to you guys.